Hi, mathletes. Today we're going to have an introduction to probability. Probabilities can range anywhere from 0 to 1, and the closer you get to 1, the more likely the event will occur. So we use probability as fractions, decimals, or percentages. Here's an example. Let's say something is impossible, it cannot happen. We'd say the probability is 0 or 0%. So if it cannot rain, you're in the middle of the desert and you know there is no chance of rain, we'd say that there's 0% or it's impossible. If it's unlikely to happen, we'd say that it has a probability of 1/4, or we could say 25 hundredths or 25%. It means it's probably not going to happen. So if you're planning on having a picnic and you hear that there's a 25% chance of rain, it probably isn't going to happen. So it's safe to have your picnic outside. If it occurs half the time, we say the probability is 1/2, 5/10, or 50%. So that means it might rain, but it has an equal probability that it's not going to rain. So sometimes you hear people say it has a 50-50 chance. If it's likely, we'd say the probability is 3/4 or 75 hundredths or 75%. So in this case, you might want to bring your umbrella because it's a pretty good chance that it's going to rain. But definitely bring your umbrella if it has a percentage of 100 or the probability of 1, because that means for certain it's going to rain, and it probably is raining right now. The probability of something is the number of successes over the total possible outcomes. So, for example, let's say that you're rolling a number cube and there's 6 numbers on your number cube. What's the probability of rolling a 3? Well, there's only one 3, but there's 6 total possibilities. So it would be 1/6. Again, there's only one number that would represent a success, which would be the number 3 out of 6 possible numbers. The probability of rolling an even number? Well, 2, 4, and 6 are even numbers, so 3 out of 6, which we can simplify to 1/2. The probability of rolling a number less than 5, well, that would be numbers 1, 2, 3, and 4, so 4/6, which we can simplify to 2/3. Now let's look at some spinners. Let's try to figure out the probability of getting a blue. Well, on that first spinner, it looks like it's 1/2 because 1 out of the 2 colors is blue. The second spinner, also 1/2. And the third spinner, there's 3 colors, so 1/3. Of course, if it was always this easy, we wouldn't have to study probability. So we can figure out probability by experimenting, by doing it. So let's play a game. With this game, we're going to spin the spinner twice. If you get 2 matching colors, you win. So what's the probability of winning? Well, it would be 1/2. Let's do the experiment. And we're going to play the game 10 times and record our results. And here's what the table looks like. If you want to play along, you can actually make this table on your paper, grab a paper clip, and then put it on your spinner. And you can use a pen or pencil to put right here in the dot, and then you can just click the spinner and then record your results. You might want to pause the video here so that you can play the game. And then when you're done, let's see how you did. So I just finished playing, and this is my result. How many games did I win? Well, I actually won 7 games, and again, I played 10 of them. So the probability of me winning, according to this game that I played, is 7/10. But I know I'm supposed to get 1/2. 7/10 is not the same as 1/2. It's bigger. I know that 1/2 is 5/10. So I won 2 more times than I should have. So I thought maybe 10 games isn't enough. So I decided to play 100 games. And I recorded my results in a table using the 10 game increments. So here we go. The top row is how many times I won. The middle row is how many games I played. And then the bottom row is the probability of me winning. So you can see 7/10 was the first time I played. You'll notice that some of the denominators look a little different, and it's because I simplified them. So 48 100ths is the same as 12 25ths. Then I decided to graph my results, and I got something that looked like this. So what do you see? What do you think? And what do you wonder? You might want to pause the video here so that you have some time to look at the graph, come up with some ideas. Well, when I looked at this graph, I thought of the law of large numbers. And Jacob Bernoulli is the one who came up with it. And he first published this in 1713. And what the law says is that the number of trials, as they increase, the experimental probability gets closer and closer to the theoretical probability. So you might be wondering, but what does experimental and theoretical probability mean? Well, the experimental probability is what we just did. It's what actually happens when we were playing the game. But most of the time we use theoretical probability, and that's what should happen in theory if we do some calculations. So here's an example of using the theoretical probability. Let's say we have two independent events, like the game we just played, where we were spinning the spinner twice. We can figure out the theoretical probability by making this table of outcomes. So in this table, I'm going to put the possible outcomes for the first event across the top. So my first spin, I could get a red or a blue. Then my next spin is going to go on the side. Again, I could get a red or a blue. And now I can fill in all the outcomes. I could get a red and a red. I could get a blue and a red. I could get a red and a blue. Or I could get a blue and a blue. So how many possible outcomes are there? Well, let's see. 1, 2, 3, 4. So there's 4 outcomes. And how many are matches? Well, here's a match, a red and a red and a blue and a blue. So 2 are matches. So the probability of winning is 2 out of 4, again, which is the same thing as 1/2. I just simplified it. So now let's play the game again, but this time let's use spinner 1 for my first spin and spinner 2 for my second spin. The table looks exactly the same, and now we're going to fill it in. Again, if you want to play the game, just pause the video here, and then when you're done, you can start it again. So I just finished playing, and how many games did I win? Well, this time I only won 3 games. And again, I played 10, so the probability of me winning is 3/10. Now let's calculate the theoretical probability. So again, my first spin, I could get a red or a blue, but my second spin, I could get a blue or a green. So I could get a red and a blue and a blue, a red and a green, or a blue and a green. So the probability of winning the game, well, there's only one match, so 1/4. That's not consistent with our experiment, was it? No, matter of fact, I got 3/10. So why is mine different? Is it possible to get 1/4 if I'm spinning it 10 times? Again, you might want to pause here and think about it. Spinning it 10 times, can I get 1/4? If you're starting to think about multiples of 4, you are on the right track because 10 is not a multiple of 4. So it's impossible to get 1/4 when you're having 10 as a denominator. You'd need to play 8 times, 12 times, 16 times. In other words, your 4 multiplication tables. So if I think of it, if I played 8 times and won 2, that would be 1/4. Or I played 12 times and won 3, that would be 1/4. Or 16 times and I won 4, etc. Now let's find the probability of winning the matching game, but instead of doing experimental probability, let's just do theoretical probability. So we're going to spin spinner 1 or spinner 2, and then we're going to spin spinner 3. So the first outcome would be a blue or a green, and the second one would be red, yellow, blue. Notice I have 3 different colors, so I needed to have 3 different boxes. Now I can fill them in with blue, red, blue, yellow, green, yellow, blue, blue, and green, blue. And again, how many are successful? Well, just the one. And how many games did I, or how many outcomes are there? And it looks like there's 6. So the probability of winning is 1/6. Now let's calculate the theoretical probability of a family with 2 children and both of them are boys. So just like before, the first outcome, it could be a boy or a girl. Just like with the spin, we could have blue or green. And then for the second child, it could be a boy or a girl. So we could have a boy and a boy, a girl and a boy and a girl, or a girl and a girl. So for them both to be boys, well, it looks like there's 4 possible outcomes and only one of them has the 2 boys in it. So it would be 1/4. Does this surprise you? Did you think the probability would be higher or did you think it would be lower? Well, let's do the same thing, but this time we're going to look for 3 children. And we can use what we call the table method twice. So this is the one we just did. Now we're going to use these results for these children for the top, because that means that the first two children could be boy, 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 girl, or girl. And the third child, again, a boy or a girl. So now we can fill these in as boy, 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 girl, boy, boy, girl, boy, girl, boy, girl, boy, boy, girl, boy, girl, or all girls. So now, what is the probability that this family with 3 kids has all girls? Well, only 1 out of 8, because there's 8 possibilities, but only one has all girls. What about that the oldest is a girl? Well, let's say that the last one was the oldest. 1, 2, 3, 4. So 4 out of 8, or 1/2. What about exactly 2 boys? Well, this has 3, so that wouldn't work. So it looks like there's 1, 2, 3. So 3/8. How about at least 2 boys? Well, this one I could count now. So 1, 2, 3, and 4. So it looks like 4/8, or 1/2. So now, based on what we just did, do you think that you could calculate the probability in a family of 4 kids that all 4 are boys, but don't use the table method? Can you come up with some sort of a pattern? Well, I noticed that when I did this one, I noticed that you could have a boy or a girl, a boy or a girl, or a boy or a girl. So there were 2 different options. So I thought, what if I said 2 multiplied by 2 multiplied by 2 multiplied by 2? Since there's 4 children, 1, 2, 3, 4, and 2 possibilities. So that means that there'd be 16 of all the outcomes, and only 1 is all boys. So 1/16. So what's the pattern? See if you can come up with it. Well, here's what I came up with. I said 2 to the power of the number of children tells you how many outcomes there are. So I wrote it now this way, a little shorter version, so you can see it's an exponent. And to show you how this works with the one up there, we would have 2, because again, it could be boy or girl, to the power of 4, because there's 4 children, is 16. Now, could you create an expression to find the possible outcomes for all different situations, not just for boys or girls? And I'm going to let you think about this one. So pause the video, think about it, and then come back. So here's what I figured out. I said, well, you can have different choices. Like in this case, we had boy or girl. And then you would repeat the time. So here I repeated it 4 times because there were 4 children. So what if I said n equals the choices and r equals the repeated times, and then I can use n to the power of r, which is a lot easier to write than all of these letters. Well, let's give it a go. Let's practice our expression. So let's say that we were rolling a 6-sided number cube and we rolled it 3 times. What's the probability of getting a 5 every single time? Well, we know that we're going to use n to the power of r, where n is the number of choices. And how many choices are there? Well, there's a 6-sided number cube, so there's 6 different numbers I could get. I could get 1, 2, 3, 4, 5, or 6. And how many times am I rolling it? 3. So 6 cubed. And 6 cubed is 216. So there's 216 possible outcomes. And I want to get a 5 every single time. Well, that's only going to happen once. So the probability is 1 out of 216. Oh, I don't think that that's very probable to happen. I think that that would be really, really rare. I hope that helps you understand a little bit about probability and the difference between experimental probability and theoretical probability. If you enjoyed this video, I suggest you look at my other videos. I have them on statistics and probability, but also on some other strands of mathematics. As always, thank you so much for watching.